Hello everyone, this is video 6.3. We're going to be looking at the standard division algorithm, what the book refers to as the scaffold algorithm. We'll talk about why it gets that name here in a moment. If you have any questions from video 6.2, hopefully some of them will be resolved in this video. And then if there's anything that you have, any questions you have from 6.2, 6.3 kind of combined, I can certainly bring those to class and we'll get those answered. So let's get started. So, as a quick review, a couple of things that we're probably going to need before we get too far into this. Since we're talking about an algorithm, we haven't talked about an algorithm in a while. So, an algorithm, remember, we think of as simply a step-by-step process for solving some sort of problem. We've looked at the multiplication algorithm, we've looked at algorithms for carrying and borrowing. We talked about as regrouping. So we're just laying out a series of steps. Do these things and get this answer. That sort of approach. So that's an algorithm. The measurement model and the partitive model we talked about in the previous videos. Remember that the measurement model is where we are measuring out from our original amount. So we have our dividend, and we're going to measure out the divisor from that. And the number of times we can take that divisor is going to be our quotient. So the number of groups that we can remove, the number of measurements, will be our quotient. If we get a remainder, we'll worry about that at the end. The remainder is not going to be a whole lot different now than it was in video 6.2. The partitive model is where we know the number of groups. So we have our dividend, and we're going to partition it into the divisor number of groups. And so what we want to do is we want to find the size of each of those groups. We want to know how much will go into each of those groups. So hopefully you remember that the measurement and partitive model are going to yield the same answer. So if I solve a division problem in either of these two ways, I shouldn't get a different answer. This is a different way of thinking about and sort of representing the division that's taking place. And so in the problems that we're going to look at, the examples that we're going to see, I'm going to go through both models for the first couple of examples so we can see how this process works. So let's look at the first example. So I want to look at 64 divided by 4 and using the measurement model. Now, the most concrete way to do this would be to take 64, and we could literally draw out 64 individual X's like this. I mean, this would probably be the most concrete way to do it. And then just start measuring off, well, here's 4, and then here's 4, and then so on, so on, so on. It's not going to take long before we kind of see how unwieldy this process is. Number one, it's a lot of drawing. I mean, we got to write all these little X's. Or if we were using base 10 blocks, I got to get 64 unit blocks out and then start to count these off in fours. So it's not the best process. If we were using base 10 blocks, hopefully this would get us to thinking about, instead of using 64 units, so we'll go from 64 units to 6 tens and 4 units. So we're going to use this sort of expanded form to think about this division problem. So I want you to take a second to appreciate that when we did the multiplication problems, we use expanded form to make this make a little bit more sense. That expanded form gave us that rectangle, allowed us to break that rectangle into those different regions, and then sort of give us some structure to how we did that multiplication. And that structure became the algorithm. And so the same thing is going to take place here. We're going to use this expanded form to isolate place value and then do the division that way in this sort of structured way. And then division along that structure is what's going to give us the algorithm. So it's not exactly the same process. It's not identical, but it definitely rhymes. And hopefully you can see the importance of establishing ideas like place value and expanded form from very early in the semester, coming back and using those ideas for something like division. You may not immediately see how these two ideas are related, but hopefully this class gives you some sort of insight into how these early ideas like place value and expanded form come back in and are helpful later on in something like division. Anyway, so let's draw this out. We got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So now we're measuring off in fours. So the big abstraction that's going to take place here is to think about what we mean by measuring off fours or measuring off groups of four, because it's not just 4 units, it's any group of 4 things that are identical. So these 4 tens could form a group. So I'm going to measure off these 4. And so this is, we're a measurement model. We know how many we are measuring off, but we want to know how many groups there are. And so since we have these as tens, we've essentially taken off 10 groups at one time, right? And so if we wanted, we could push those long pieces together and see as we count across the 4 dimension of the rectangle that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that makes 10 groups right there. Now these tens here, we don't have enough. There's only 2 of them. So they're going to break apart and they're going to make 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. There you go. So now we've got these 24 units. These tens broke up because we didn't have enough tens to make another group of tens. So now I've got these 24 units. And so there's one group, 2, 3, 4, 5, 6. And so there's 6 groups here. So we're measuring just like we did before, but now we're thinking about measuring in a little bit more expansive of a way, that I'm not just measuring off units, but I can measure off tens, hundreds, thousands. I can measure off in whatever place value I want. And so I got 10 groups here, 6 groups here, and so I get 64. Let's switch. 64 divided by 4 equals 16. So that's my quotient. I've measured off in groups of 4. I ended up with 16 groups. That's my quotient. I can also do this problem using the partitive model, and in very much a very similar way. Again, I could start off in this really concrete form of taking 64 individual blocks and putting them into 4 columns. Again, the unwieldiness of 64 tiny little pieces is probably going to be compelling for us to think of this using place value. So I got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And so here I've got my 64, and I want to partition this into 1, 2, 3, 4. So here's my 4 columns. And so again, we want to be expansive in how we think about what this partitioning is going to be and what can go into those partitions. And what we saw in video 6.2 was that we were putting one piece at a time in there. But once we get up to 64, it should motivate this abstraction to thinking about putting things in these partitions other than just units. So I can put these tens in here also. So let's switch back to green here. So we've got 1, 2, 3, 4. And so that takes care of these 4. They've been placed. Now, I can't put another 10 into each group. So if you think back to our remainder conversation from 6.2, I don't have enough to do another complete group, so I know I'm going to have to stop. And so these won't become part of a remainder, though, because they can be broken down. So they'll get broken down into the same sort of picture that we had on the previous slide. So now I have 24. And so I can place 1, 2, 3, 4. and those are all placed. 1, 2, 3, 4, and those are all placed. And I can keep doing this. 3, until these all find a home. 4, and now I'm down to 4, and they evenly distribute out, and I've gotten down to 0. There's no remainder. Now, I knew I wanted to start off with 4 groups. Now I'm going to count how many is in each group. I have a 10. I have 6 ones. That also makes 16, just as with the measurement model. In going through the process, marking off these sort of 4 at a time, it may feel like measurement because we're kind of taking off 4 at a time. But the reason we're taking off the 4 at a time is because that's the number of groups that are established. So even though some of the process may feel very similar to the measurement model, it is conceptually different. It is a different model. So we can extend this to a problem like 744 divided by 12, where now we're going to be dividing by a 2-digit number. And I've gone ahead and drawn out the 744, so you don't have to watch me do that again. So when we're dividing by 12 using the measurement model, a couple of different things we have to think about now as well. So not only can we be a little bit more flexible in how we think about this measurement piece, but being a little bit more flexible in how we think about that 12. And so, again, in the previous problem, the 6 could also be a 60. That it wasn't just taking 6 units, but that was also taking 6 groups of 10 or 6 groups of 100. In thinking about this 12, we can think of it as 12 groups of a unit, or 12 groups of 10. But 12 groups of a unit would really be 1 10 and 2 units. And 12 groups of 10s would really be 100 and 2 10s. Now, if this is a little bit of a leap for your students, or maybe even a little bit of a leap for you right now, if this is your first time seeing it, you can certainly break all these things down into 12 actual pieces. So the way that I'm about to kind of show you this problem, I'll show you sort of a side road you can take that's a little bit more concrete. So it's a little bit more abstract. I'm sorry, it's a little bit more concrete of an approach. If you go all the way to the most concrete version, we need 744 units. But again, that's probably more than that I want to draw and that you want to watch. So using place value and using these groupings allows us for a little bit more efficient and expedient of a solution. Anyway, so my 12, I'm going to start off, let me switch back to green. So I'm going to take this piece and then 2 of these 10s. And so they're going to form this group. And this is a 10 because, or this is a 12 rather, because it is 12 here. So we've got 10, 1, and then 2. So that all together makes 12. And so we're counting my 12s here across here. So you can see how this makes a 12. Now, each one of these groups is essentially a 10 because I have 10 of these 12s kind of stacked up. And so one way to think about this that might make it a little bit easier to visualize is you could put all these pieces together into a rectangle. And so you can see that this is a 10, this is a 12, this is a 12 along here. I don't know if this 10, 1, 2 is helping or not. So this is a 12 along here, and we know this is 10 because this is a 100, this is a 10, and this is a 10. So we can see that this is 120, this is a 10 by 12. And so this is 10 groups of 12. So this is 10 groups of 12. I can do the same thing here, and then take these off, and so there's my 100 with 2 10s, so that's another 10 groups of 12. And well, now I've got 1, 2, 3, 4, 5 groups of 10, so I can't take any more 12s. But when I run out of these groups, I can always ungroup something. So I'm going to ungroup this into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to break this into 10 tens, this 100 into 10 tens. And so now I can take another group of 12. I can take another group of 12. It's another 10 groups, another 10 groups, another 10 groups of 12. And then another 10 groups of 12. And so I've got 60 groups of 12, but I've also got these 2 10s and these 4 1s left over. So now I can't do anything more with these hundreds, and I can't do much else with these 10s except group them with these 1s. And so if I were to move my pieces around, then I see that I've got a 1 and a 1, 1, 2, 3, 4. So I see that I've got 2 groups of 12. There's 1 group of 12. There's another group of 12. So if I add this up, I've got 10, 20, 30, 40, 50, 60, 1, and 2. So I've got 62, 744 divided by 12 equals 62 groups that I've measured out by 12. I've just made the counting a little bit easier by taking these groups here, 10 at a time while I could. And then once I ran out of groups of 10 at a time that I could take, then I took my 12s one at a time. It's a little confusing because we're talking about groups sort of on 2 different levels. We're talking about the groups of 12 that I have to measure off as the division problem, but I'm also talking about groups of 10 because that's inherent to place value. So we're talking about groups sort of in 2 different ways at the same time, which can be a little bit confusing. But I think once you see this rectangle, then you kind of get the idea that we are still talking about groups of 12. That's still the primary idea, but just I'm collecting them in larger groups or larger sets at one time to make the counting a little bit easier. But this is this division problem, 744 divided by 12, taken by the measurement model. Now, if we look at the same problem, the 744 divided by 12, using the partitive model, we're going to see sort of a shortcoming, sort of a little bit of a flaw in the partitive model with 2-digit division. Because I want to put these things into, I want to distribute these pieces into 12 different groups. Well, I can't really have 12 of these pieces naturally the way we would most sort of naturally write it, because once we had 10 of something, they would group into the largest piece. So what I could do is take, and I'll switch back to green here, I'll take this 10 and I'll start to just count it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that gets me to 10, as I would imagine. So I'll take this 10 and starting at the 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, so starting here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One more time, 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, let's fix that. 9, 10. Do 10 more, and that should get me to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. Now I can start to do this again, but when I break this down into tens, I might notice that all of this sort of makes a 12. So I'm just going to ungroup all of this together and everybody gets a 10. And now this 24, if I would distribute, again, I could break this 10 into units. So this 10 gets broken into units, and so does the other 10. And so then when I distribute these 1, 2, 1, 2, I can distribute these 2 at a time just to make things a little bit easier. And I get the same thing. So there's a little bit of ungrouping that has to be done as I'm doing the distribution, as opposed to the measurement model where I can just sort of group these things together and then count them off, and I don't have to ungroup them until the end when I run out of uh, the group size that I'm looking for. So it makes it a little bit more complex. There's a little bit more moving parts. There's a little bit more to contend with. It's still doable. It's still a very viable model. And like I mentioned in video 6.2, there will be students for whom the partitive model makes a lot more sense over the measurement model, or vice versa. So it's worth being able to show both these solutions. But for me, the partitive model is a little bit more unwieldy once we get past dividing by 10, once we get into two-digit numbers, because it's hard to make those groups, the number of groups, work as easily. So now we can define this scaffold algorithm now that we've sort of seen all the conceptual pieces building up to it. If I were to take this 64 divided by 4, which is the first problem that we looked at, so I divide the 4 into the 6. Now again, we should sort of recognize that what we're really doing is we're dividing the 4 into the 60. And as you might imagine, we can take this problem and break it into this expanded form and do the 4 divided into the 60. So it's more explicit that we're dividing the 4 into the 60. But really what I'm taking is how many groups of 4 are in 6, or how many full distributions across 4 groups could I do with 6? And either way that I conceptualize that, I'm going to get one way of doing it. So I'm going to write this quotient part, the number of groupings or the number of distributions across a fixed number of groups, along the top. And so now, how many did I measure off? Well, I either measured off 40 of them, or I distributed 40 of them. So again, depending on which model you're using and talking about, we're going to think about this 4 in a slightly different way. And again, if we want to be more explicit about it, that is not really a 4 any more than that 6 is really just a 6. This 6 was really a 60, and this was really a 40, and this was really a 10. I did 10 groups of 4. Well, that makes 40. Then I'm going to subtract from that 60. I can't take any more because that would be 80, and that's too much. I can't take any fewer. Well, I could take fewer, but it'd be kind of silly to do. Um, so as the algorithm goes, I couldn't take fewer. So I want to take 10 groups of 4, because that 40 leaves me with 20, which is where I want to be. We talked about in the last video with that remainder spot. I want to try to get to 0, but I want to make sure that I'm less than what I'm dividing by. So I subtract this off and get this 2, which was also really a 20. And now this is the part that we really have to talk about, because this is the part that a lot of students really find a little confusing, is bringing down this 4. And so, well, why do we just magically bring down this next number? Well, what it's really doing is it's breaking down this 2 from from 2 10s to 21s. And so by bringing down that 4, I've sort of recentered the place value from where we're talking about tens to we're talking about units. And so now this 2 went from being, like I said, 2 tens into 20 units. And now 4 goes into 24. That goes in 6 times. So 4 will go into 24. Well, it would go in here 5 times and then 1 time. So I could write this as 5 plus 1, or just 6. And so that's 24. And so that leaves a 0. This is 24, and that leaves a 0. Um, sorry, this sometimes people write a line there, and we'll write it as a 0 instead. And so this is what this scaffold algorithm shows. It's not any different than what we did modeling with the measurement method and the partitive method. We're still looking at taking these sets out or doing distribution across a number of sets. Again, I've said this a bunch of times this semester already. It's not that the algorithm is bad, but that the algorithm needs to be supported by something. So starting with those models, building into the algorithm is going to allow the algorithm to make a lot more sense for students than just starting with the algorithm and saying, do this, do this, do this, bring that 4 down, and don't wonder, don't ask why we do it. So this is a scaffold algorithm. I'll skip the 744 problem that we did before. If you need to practice with the scaffold algorithm, I'll let you do that, but we've already seen the answer and the way that sort of works. So I'll leave that scaffold algorithm example for you to do. The next example will give us an opportunity to practice it a little bit more as well. So the last example I want to look at is just 15 divided by 4. And this is going to allow us to convert a division problem, inherently a fraction, this 15/4, into some sort of decimal. I could do the same thing with 1 divided by 4 or 3 divided by 4. So I'm using an improper fraction, not for any specific purpose. But if I take this 15 divided by 4, and I'm going to do this after I've done this scaffold algorithm, because this would be a really unwieldy problem to do concretely, because for reasons you'll see here in a moment. It's going to require a lot of ungrouping that physically we might have a really hard time doing. So we need a base level of abstraction before we can really do this type of problem. So 4 will go into 15 3 times. That's a 12. And so 4 times 3 makes 12, so there's 12. And so now if I subtract this off, I get 3. And so we talked about in the previous slide, I could just say remainder 3, or I could say 3 3/4, and we would all hopefully recognize that 15/4 is the same as 3 3/4. But what I could also do is add this decimal point and a 0, and 15 is the same as 15.0. And so now I'm going to make this problem not about 3 units, but about 30 tenths. So let me make this more explicit. So I've gone from this being 3 to essentially 30 tenths. And why 30 tenths? Well, because I can't divide 4 into 3. But by shifting the place value over, now instead of being 3 things, I have 30 things, and I can divide 4 into 30. I know I can do that. So 4 will go into 37 times. And so 7 times 4, that's 28. And so this is really not 7 times, but 7/10 of a time. And 7/10 times 4 is really 28 tenths. So I can keep my decimal points all sort of in line now, so I can see that this isn't really 30, it's 30 tenths. So this isn't really 28, it's 28 tenths. And so when I subtract, I get 2 tenths. Now we're at the same problem we were at before. 4 won't divide into 2 tenths, but I can add a 0 and make this now, we've gone from 2 tenths to 21 hundredths. And again, 4 won't go into 2, but it will go into 20. And so by adding that extra 0, shifting that place value, I allow this division to keep going. So 4 will go into this 20 5 times. And so we know that's 5 hundredths. And so 5 hundredths times 4 makes 20 hundredths, which is the same as 2 tenths. And that gives me a 0. And so now I'm done. We hopefully know from what we talked about in the previous slide when we talk about doing division, we either want to get to where we get to a 0 or we get to a remainder. In this case, when we got to a remainder, we just added on a 0 past that decimal point to keep going until we got to where it would terminate. Now, later on in the semester in another chapter, we'll talk about how not all these things will terminate. We'll come to this a little bit later on. This was a special case that I picked that I knew would, because that suits our purposes for right now. But later on, we'll talk about some things that don't. And most of you already know, like 1/3, 2/3, 1/6. A lot of these decimals don't terminate. In other words, they just kind of keep going. But for right now, for what we're talking about, this will suffice. So again, this thing of like what is adding on a 0 and bringing it down, most of us learned as kids to just do it because we were told to do it. But if you think about what we're doing with that, and you think about how we're using equivalent fractions essentially in this case, that process should make sense. At least I hope it makes sense. All right. So for your checkpoint problem, I want you to model and solve 322 divided by 7 and 322 divided by 14. The 7 is a single digit, so you've got a little bit more flexibility in how you can think about that. The divided by 14, because it's two digits, like we talked about, is going to be a little bit harder to do from the partitive model, but you certainly can. I certainly want you to try. And so I'll leave you with these two problems to think about. If you have any questions about these two problems or anything else that we've talked about from this slide or from any other previous slides, by all means, please let me know. All right, thank you.